Okay, so it's 20 of. Is everybody all set? As ready as you're ever going to be? Okay, I do have one announcement, and I'm going to be really, I apologize in advance if this makes anybody upset. But I decided, since we had a really long sort of class today, class 8 has a lot of material, that I would give you the quiz as a take-home quiz. Is that okay?
Yes. That's okay.
That's okay? Is anybody upset by that? You upset?
No, she's not.
No? Okay. And so there's only, no, exactly, thank you for saying that, teamwork. The only exception, I want to read you the instructions up here. You can use whatever resources you want for this quiz, except the help of another person. Okay? You can use your books, you can go online, you can use your homework, anything you want, but do not talk to anyone else about the quiz. Do not compare answers when you come in on Monday, okay? Let me address Sam's comment. I studied so hard. Guess what? That's fabulous, because now you won't have to take all weekend to do the quiz, because you studied hard. You're ready for it. Take it as soon as possible. Don't put it off, because everything's right there. Right after class, you could stay here and work on it. All right. So I want you all to listen to this next thing, please. I know you're all excited. Okay. When you're ready, I'll let you know what I want to say. This is due at 10:40 on Monday. Not at 11 o'clock, not at 10:45. If for some reason you know you're not going to make it, scan it, do cam scanner, take a picture with the computer, come in on Sunday, put it under my door. If I don't have this in your blue folder at 10 o'clock, 10:40 on Monday, it's a 0. Okay? So I will hand these out at the end of class, so let's start today's class. Has anybody in here, in the mathematics you have seen previous to stepping in this class, has anybody never seen I, the number I? I'm not saying do you remember what it is, but has anybody not ever seen I in their life? Yes, no? Don't remember? Talk to me. No, I don't want you to remember any details, but have you ever seen an eye before, Anna? Yeah, okay, that's all I'm asking. Anybody not seen eye before? All right, so I'm going to try to, I won't go into a song and dance about it. I'm just going to sort of give you the definition, and we're going to see how to use it. We're going to see how to add, subtract, and multiply with I, and then we're going to apply what we find to solving quadratic equations. Ryan, were you able to get any music from either one of those? Huh? No, the second link didn't work. The first one had a link to it. Yeah. Can you do a little search for me? Can you find the melody for Pup Goes the Weasel? Since my links don't work anymore. All right. So the letter I is a number that has this definition, and that's exactly what it is. It's a definition because it was invented. It was invented by mathematicians because they were frustrated. And so now we can be frustrated, right? They were frustrated because one of the equations they couldn't solve was the following. They could not solve this equation with real numbers because there's no real number that you can square and get -1. Or if you took the square root of x squared, there wasn't anything to call the square root of -1. So the real number system that we know that has real numbers and rational numbers and irrational numbers, that makes up the real number system. So they decided to make this number system bigger by introducing this new number. called I. I is defined to be the square root of -1. So if we ever are asked to take the square root of a negative number, the first step that we do is we factor it to be the square root of -1 times the square root of k. So we pull out the -1 as a factor. And then where we see the square root of -1, we throw the I in front of the square root of k. And that's where the I always sits. If the square root of k is irrational, like square root of 7, square root of 13, we usually keep the I in front. But notice this is multiplication, so you're not wrong if you put it to the right of it. It's just sometimes it's not clear the way people write whether that I is tucked underneath or outside. So to sort of like not have like scribbly writing, when k is an irrational, when square root of k is irrational, we usually put the I in front. If k was something like the square root of 100, we'd call it 10, and then we might say 10i. Then there's no problem understanding what you're representing. So let's take a look at the next two things here. Square root of -49. So let's follow the little definition we have right here. So we're going to make this into a multiplication problem. And we're going to pull the -1. So essentially what we're doing is we're changing -49 to look like this. -1 times 49. So we take the square root of -1, and then we take the square root of 49. And then we replace the square root of -1 with the number I, and we replace the square root of 49. Since 49 is a perfect square, we get 7. And you could leave your answer like that, I times 7, or you could say 7i. Either way. It's just all multiplication, so the order doesn't matter. Any questions on that one? All right, I need your help with the next one. Can someone help me with the next one? What maybe my first step would be, and then I'll simplify from there. Anna? Two I. Ooh, she's going right to the end. 2i, and then what? And what was left underneath the radical? Radical 2. So she did that. How many people got that just like that? 2i, radical 2. All right, we're done. And no explanation, right? I mean, that's great. Anna's got special powers. I don't know about you, but I think I need a little more explanation for how she got 2i radical 2. Anybody else need a little explanation? Yeah, okay, good. So let's take a, hey, how would we check this? How do you check the answer to a square root? How do you check whether an answer to a square root is correct or not? Not a hard question. You square it, but we're not ready to square it just yet. Okay. So does anybody else want to take us maybe through some baby steps to get to that answer, 2i square root of 2? Looks a little scary to me. Caitlin?
Well, since it's a -8,
All right, so let's put that part in first. We got the square root of -1 times what? Okay, so Caitlin says we know we're going to have a -1 there, the square root of -1 as a factor. And since I know that, I'm going to skip, most of you will start skipping this step that I've just done right here. You know, as you start to feel a little more at ease with these, and you'll just throw an I there. And some of you will stop there, okay? But the radical is not as simple as possible. Katie? Right. So what you do is you bust this radical up into two equivalent radicals. Again, you're multiplying everything, where one of your factors is a perfect square. You're looking for a perfect square that divides 8. And you see there that this is what makes you very happy, the square root of 4. There's where your 2 comes from. You can put the 2 beside I in any order. And then square root of 2 is always going to be irrational, and it's always stuck under that radical sign. So that's how you get 2i square roots of 2. Any questions on that? All right. Now, how do we figure out what I square is? if I is equal to the square root of -1, how do I figure out what I square is? What would I do to both sides to find I square? How do you go from I to I square? What do? You square it, right? So let's square both sides, because I'm trying to find out what I square equals. So here's I square. So what's the square root of anything squared? What happens? Think of any number you want instead of -1. What happens when I take the square root of something and then I square it? Where do I come back to? The number under the square root. Does anybody know the name for the number under the square root, what we call that? Radicand. Wow, I'm so impressed. Radicand, right. You come right back to the radicand, because squaring something and square rooting something are inverse operations. They undo each other. So I square is equal to a -1. So I square equals -1. This you want to put in like big bold box with lots of stars around it. You're going to use this forever and ever today and in your homework. This is a really very useful power of I. And if you wanted to, you could find I to the third, I to the fourth, I to the fifth. You could play that little game with yourself and see what you discover. But I squared is going to equal -1. So if you wanted to check, say, your answer to number A, you're saying that 7i is the square root of -49, which means if I were to square 7i, I better come back to -49. So my exponent rules, I have a product to a power. So I apply the 2 to each of these. I get 7 squared times I squared. 7 squared is 49. I squared is -1. It checks. Okay, so you can check your answers now that you know what the value of I squared is. Any questions on that? Those 3 problems? All right. So here's what I was talking about earlier. We've expanded our real number system now to include this bigger number system called complex numbers. And if you have a complex number, it can either be represented as a real number or an imaginary number. And a real number is when this value b is equal to 0. Because when that's equal to 0, notice you just get 5. So all numbers can be represented like this, a plus bi. And if b is equal to 0, then it's a real number. If b is not equal to 0, then it's what we call an imaginary number. Okay, so 2 plus 5i is an imaginary. It's part of the complex number system. 3 minus 4i. 5 plus 0i. It's complex. We can say 5 is a complex number, but we know it more familiar. We're more familiar with it as a real number. Okay. So we can add, subtract, multiply, and divide with these numbers. And so if I asked you to simplify the following, and you looked at A here, what kind of operation are you doing between those 2 complex numbers? What's your operation there? It's not FOIL, because if it was FOIL, I'd have to be multiplying, right? What operation am I doing here with these 2 complex numbers? Addition. So what's the key thing about adding in algebra or arithmetic when you add anything? What do you always look for when you add, Katie? You want things to be like, right? You want them to be like, combining like terms. So I can drop these parentheses. I won't get arrested if I drop the parentheses, because nothing's happening outside of them. So I'm just going to drop these parentheses and see that I have 4 terms here. I have 4 terms. And now I ask, do I have any like terms? That's the question. And I heard a yes from the peanut gallery. And what like terms do I have from someone other than table 2? What like terms do I have? Jesse? 3i and 5i. Those are certainly like. Yes, these are like. Someone else for any other like terms?
2 and 1.
2 and 1. Alike. So we add the 2 and 1 and we get 3. We add 3i and 5i. We get 3 plus 5 times I, which is called 8i. And we're all done. That's it. Life is good. We can handle that. Yes? Okay, you do the next one. Answers for this one. I may get more than one answer, so we'll see. So answer or answers. So any volunteers? Ryan, what you get? You didn't volunteer. I volunteered you. Sorry. Yeah. You got 1 minus 2i? Okay, who agrees with that? Everybody? William, you don't agree with that. What you get, William? Now you do? You're supposed to change all the signs. So what did you have?
I had 1 plus.
Yeah. Okay, but now you see what you did wrong. Okay, good. Yeah, so this big subtraction sign there says, because the parentheses are around the 1 and the 5i, it's telling you subtract the 1 and subtract the 5i. So when you drop the parentheses on this second term, you will be put in jail if you don't subtract both of those. Okay, so that's 1 minus 2i. Any questions on that? Okay, Jesse, now's your turn to shine. You can now use FOIL on this one because now you have a binomial times a binomial. So this is just like any other FOIL problem or any multiplication problem of a 2-digit number times a 2-digit number. So you do your first term times your first term, which is 2, your outer term times your outer term, which is 10i, your inner term times your inner term, 3i, and then finally 3i times 5i. 3i times 5i gives me 3 times 5 times I, which is 15i squared. A lot of i's. For your eyes only. All right. Do I have any like terms here? Yeah. Usually our like terms are the middle and the outer, right? We usually get to put these together. 2 plus 13i plus 15i squared. And now you say, hey, I have an I squared that's different than an I and it's different than a constant. I'm all done, right? What? You learned what? What? The I square is -1, right? Yes, help Katie remember. Yes, 13i. So where you see the I square, you can replace it with -1, turning that into a real number, and you get 13i minus 13, or -13 plus 13i, however you want to write it. They both say the same thing. All right. You try the next one at your seats. Take a look at this. The answer that you should have arrived at, which is kind of quite surprising, is 13. This is equal to the number 13. So let's see how we got that. 2 times 2 is 4. 2 times -3i is minus 6i. 2 times 3i is plus 6i. And 3i times -3i is minus 9i squared. Any questions so far? Any questions there? Now, anytime you multiply two factors that look identical, except for one's addition and one's subtraction, you're always going to lose that middle term. The outer and inner will always give you 0 because they're opposites. They have the same numbers except for their opposites. So this goes to 0, and this gives you 4 minus 9i squared. But we now know I squared is equal to -1, so we substitute -1 in for I squared, and this now becomes the sum of 4 and 9, which is 13. So the big news here, folks, is this is the sum of two perfect squares. And when we saw things like this earlier, we were told you can factor this first one, which is the difference of perfect squares, into the two factors that look alike, except for x. One is a plus and one is a minus. But we were told this was prime. Can't factor that. We know that's not x plus 2 squared. Why do we know that? Because you can't apply this, because it's not multiplication and division inside. Exponent rules don't apply there. You have to write x plus 2 times x plus 2. When you do that, you get a middle term called 4x. So I was very careful when we talked about this 3 classes ago to say this couldn't be factored using real numbers. And I said, you'll hear me say this again. You can factor this now that we have the complex number system. And it looks like this. X and x. We're going to go right back to here. We're going to have the plus and the minus, because notice we don't have an x term in the middle. But we can't call it 2 and 2. What do? Plus, oh. We can't have a 2 and a 2 in there, because that would give us, yeah, 2i, 2i. So you can factor those just as easily as you can factor the difference of perfect squares now. The signs are opposite, and it's 2i times negative 2i, which is negative 4i squared, which becomes a plus 4. So that's how you can factor the sum of two perfect squares now that you have complex numbers. Okay, so I think we're done with that page. Let's take a look at what's happening next. Okay, so I have purposely not tried to use this term because I knew it was coming in today's lecture, is that anytime you have any two factors where they are identical except for the operations are opposite, for example, addition and subtraction, these types of factors have a name. They're called conjugates. And when you take a complex number of this form and then you create its conjugate and you multiply them, you will always come up with a real number answer. Always. So we just saw that the conjugate of 2 plus 3i is 2 minus 3i. That's its conjugate. So let's suppose I gave you this, 5 plus 3i. What would its conjugate be? 5 minus 3i. And let's see if we can quickly get the answer. I know my answer here is going to be 5 squared minus 3i squared, which is 25 minus 9i squared, which is 25 plus 9. That I squared just makes that minus 9 to a plus. There's a perfect square. There's a perfect square. And there's the sum of two perfect squares. My final answer is 34. So anytime you multiply two complex conjugates, the two numbers you add will automatically be perfect squares. It's the only way. So if you got something here like 25 plus 8, you know you made a mistake because 8's not a perfect square. Okay. So here is a plus bi times a minus bi in its more general form. What's my answer to this going to be? Can anybody do it quickly? We'll do it the long way. What's the answer going to be when I get this? It's got to be a sum, right? It's got to be a sum. And it has to be of some two perfect squares. What's going to be squared in this case? A is going to be squared. The i's gone. It's the sum of the two. It's, look, if you look here, where'd the 25 come from? It was the 5 squared. Where did the 9 come from? It was the 3 squared. Where did the plus sign come from? It was subtracting I squared. So when you look at this, you get your a squared. We know our middle terms go away, and then we're left with minus b squared I squared. The I squared turns into a negative 1. So a squared plus b squared. So any two of these you ever look at, you can go quickly to this idea without having to do all your FOIL out. So if I gave you 10 minus 5i times 10 plus 5i, the first thing is that you recognize that they're complex conjugates of each other. And you say, oh, I'm just going to square the 10. I'm just going to square the 5. And then I put a big plus in front of it. And there's my answer. And if you're not comfortable doing that, then take your time and do it out with FOIL. You'll arrive at the same answer. Okay, so the last thing that I just want to cover before we go into quadratic equations is that if you were to multiply, and since someone earlier had already mentioned this term, radicand, if you multiply two quantities where the radicand underneath the, in this case, the square root sign is already negative, then you have to rewrite each of these in terms of I before you do your multiplication. Because if you didn't, this would become the square root of positive 100, which is 10. And that's not possible here. So what you need to do here is you need to change the square root of negative 20 and the square root of negative 5 so that it has an I in it. So how would I simplify the square root of negative 5 first? What would that be? Square root of negative 5 using an I. I square root of 5. And the square root of negative 20 is going to have an I times the square root of 20. I really don't have to simplify that now because now each of my radicands are positive. So I can rewrite this. This is all multiplication. The order that I multiply absolutely doesn't matter. So I'm going to do this. Now I'm going to use my product rule for radicals that says the square root of 20 times the square root of 5 is the same as the square root of 100. I times I is I square. I square is negative 1. And the square root of 100 is 10. So my answer here is negative 10. So that's the story, Morning Glory, with multiplying radicands that are both negative. Okay. Any questions on operations with complex numbers? Okay, well, let's go to something that I know is familiar to you, to solving quadratic equations. We're going to go over some vocabulary, and then we're going to look at a bunch of these. But I need to get up some kind of YouTube video here. And so Ryan told me if I go to YouTube and I put in Pop Goes the Weasel, I should get a song somewhere, right? Which one did you take?
Oh, I just did
Oh, so put instrumental in it? Okay. That's good, because I don't want the words. Free download, that sounds good. No, I don't want to download it. So in any one of these? Choose the third one? This one you like better? Why? Oh, sheet music, all right. Yeah, if you can read it, great, okay. It's really fast. I don't know if I can sing that fast. X, oh no. Okay, so here we go. Equals negative b plus or minus the square root of b squared minus 4ac all over 2a. X equals negative b plus or minus the square root of b squared minus 4ac all over 2a. Now you have to sing with me. Ha 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 ha. Do 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 do. Ready? 1, 2. Now the other time I did this, it wasn't that fast. This is like Pop Goes the Weasel on steroids. So ready? Go. X equals negative b plus or minus the square root of b squared minus 4ac all over 2a. Louder. X equals negative b plus or minus the square root of b squared minus 4ac all over 2a. Stop. Now, if I'm going to stop singing, and if I can't hear it on the playback, then we're not loud enough. So I'm not going to sing. You guys, someone's going to have to start you. Ready? Here you go. Oh, we failed that quiz. Here we go. Ready? One more time, I'll help you. Ready? X equals negative b plus or minus the square root of b squared minus 4ac all over 2a. X equals negative b plus or minus the square root of b squared minus 4ac all over 2a. You won't forget it, I promise, if you sing it. So, why try to sing something? Why try to sing something? It's a memory thing. Look at when we were really little. We learned something this long, the alphabet. Like you can hear like little 3-year-olds go A, B, C, D, right?
Yeah, but how well do you really know the alphabet?
I know it really well.
I do too. I feel bad.
Yeah, that's even better, right? I never put it to a song going backwards.
I didn't put just something backwards. Not to a song. A lot of people I show put their ABCs without the song.
You gotta have the song. I'll be with you in a minute, Katie. When my daughter was little, her last name is hyphenated. It's 14 letters long. So I put it to a song, and we used to sing it. She learned how to spell it at a very young age. So the moral of the story is you can just ignore this and think I'm crazy and all that. But I had, some of you will be singing this when you not least expect it. And when it comes to a test and you need to recall or quiz the quadratic formula, this will be one way that is guaranteed to be there in your memory banks. Katie, what were you going to say?
In high school, we were taught this.
Yeah,
And in high school.
yeah, yeah. And if you go on YouTube and you put in quadratic formula, it's really cool. They show like some students put it to like hip hop songs and they do these great dances. I mean, it's really wild what people do with this. Anyway, so let's talk about how to solve quadratic equations. First of all, these first two equations up here we call linear or first degree. First degree because why? Why do we call them first degree? They only have x. Okay, Isabel, you want to edit it? It has x. It only has x. And we don't see it, but the 1 is there. It's understood to be there. And quadratic equations, which are called second degree, I think you can see is because of this situation. Now, there's only one situation where quadratic equations have one solution, and that's where you have a perfect square on one side and 0 on the other. So that's the situation where you should only expect to get one answer. So if I had something like this, x squared equals 0, this is the only time my quadratic equation will have one answer. It's 0, because there's no other number I can put in there. Okay? Sometimes a quadratic equation will not have an answer with real numbers. But now that we have the complex number system, we should always be looking for 2 solutions to our quadratic equations, unless it looks like this. That's the only time. All right? So if it looks like this, we get one answer. Otherwise, we always should be looking on the outlook for 2 answers. So if we have some kind of perfect square equal to 0, we're going to get one solution. For example, 2x plus 3 squared equals 0. That has one solution. There's one value of x that I can put in here and have that equal to 0. And the reason is because if I write this out the long way, both of those factors are identical. So whatever value of x I find that makes this first factor 0, It's going to be totally usable in the second factor. It's exactly the same. They're identical. So anytime you have a perfect square equal to 0, your answer is 1. One answer, one solution. Not the answer isn't 1, it's you have one solution. In this case, it's going to be negative 3/2. Okay? Where are you going, Christopher?
Squares.
But don't you want this? Okay. Okay. So in general, we write square roots, this general quadratic equation as x squared plus bx plus c equals 0. This is what we call the general quadratic equation. I refer to this as a quadratic equation in standard form. We always want to have the 0 over here. And the reason we want to do that is one of the strategies for solving a quadratic equation is to be able to factor it and set the factors equal to 0. And you see this written as a principle on your notes called the zero product principle. If I have that multiplication problem, I know that the only way this equation can be true is if A is equal to 0, because 0 times B is going to give me a 0, or if B equals 0, because 0 times A is equal to 0. So this is sort of the strategy that one of the strategies we use to solve quadratic equations. And sometimes A may equal B, and they both will equal 0. Like as in this case up here, A is equal to B. So once you find the solution to one of these, you have the solution to the other. Okay, so given that most of you are familiar with this, why don't you try your hands at this first series of problems here? And then we're going to discuss them. Ask questions if you have them, and then we'll come back together as a group and talk about them. Yeah, I would put the 9 over there and make it. Yeah. And then try factoring it. Yep. Looks a lot better, except for how many answers are you supposed to get?
2.
Right. How many you got for A?
Oh.
Did you factor it? Did you bring the 9 over and factor it? What do the instructions say here? Just they didn't tell you how to do it, right? Okay. And what does that little 2 mean? That you, unless you have a perfect square equal to 0, you're going to get 2 answers. So check yourself. Do you have 2 answers? And if not, you're not getting the full boat. Should have 2 answers for all of these. All of these have 2 answers. I'm really in a like, I know, I'm acting like a little kid today, I know. when you leave. Okay, well, let's take a look. I know some of you are getting a little kerfuddled here, and oh, I forgot to shut off the recording, so that's all right. I wasn't doing anything besides making a squeaky table. Okay, this first problem is like sort of like that pain that never goes away, because you look at that and you say, you feel so confident by saying the answer is z equals 3, and you just move on without thinking. And the reason that you do that is because it comes back to how you define the square root of z squared. Okay? And I'm going to show you. And you're going to say, do I really have to do that? And the answer is no. But when you do this, the answer is not z. What? What do you mean it's not z? The answer to the square root of z squared is this. It's the absolute value of z. Because I could put 3 in for z and square it and get 9. What else could I put in for z? -3. Okay? So part of the problem is when we're taking algebra classes prior to this, books say assume z is positive or non-negative, so that you always can get away with just putting a z there. So when you get to this kind of problem, you look at z squared and you replace it with a z, and you take the square root of 9 and you replace it with a 3, and you're like golden, you think you're fine. And then I come and say half credit off, and you're like, oh, what? Oh, I forgot the -3. So I can give you a sure and fast way of getting 100% on all of these problems, or you can ignore it and hope that you remembered it has 2 answers. Here's the sure, fast way. Subtract 9 from both sides. When you do that, you're going to get the difference between 2 perfect squares, which is very easy to factor. You notice that both of these factors are different factors. They're conjugates of each other. And then it's a real simple solution. You set each factor equal to 0. And you'll get 2 entirely different answers, -3 and +3. And you will be a happy camper. Okay? If you insist on trying to remember that this has 2 answers, and hopefully somewhere in the back of your mind, when you do see something like this, you'll do this. Z equals plus or minus. Remember, the quadratic formula has a plus and minus in it. Plus or minus the square root of 9. That's the only way without factoring you're going to remember that this has 2 solutions. Okay? So I advocate this route to save you the possibility of making an error. If you insist on this route, you've got to remember the plus and minus, or you have to do this. I mean, this is really like mathematically correct. When you take the square root of z squared, you get this. When you take the square root of 9, you get that. And then you say, what can z be? Z can either be a 3 or z can be a -3. That's mathematically what's going on that arrives at this particular answer. Okay, probably more than you wanted to see. All right, so x squared equals -25. Again, some of you initially might say, can't do this because I've got a -25, but remember we have the complex number system now. So if you bring the 25 over to the left-hand side, you have the sum of 2 perfect squares, which we've learned we can now factor. The square root of x squared is x. The square root of 25 is 5. I put my plus and minus, and I throw my I beside that positive 25. And there you get your 2 solutions. When does x plus 5i equal 0? And when does x minus 5i equal 0? Well, in this first case, it's when x is the opposite of 5i, when it's -5i. There's my answer. And in this case, my answer is +5i. Anytime your factors are complex numbers, your answers are always opposite of each other. So you could put these together in one statement like this if you wanted to. Now the last one, I'm assuming a lot of you did a lot more work than you needed to. So let me show you the fast way, and then I'm going to show you the way probably most of you approached it. The fast way is C is really not any different than A and B. And you say, sure it isn't. Well, the first, there is a little bit, it's a little different, but you can make it look the same. The first difference is you've got something squared on the left side. You have a z squared here and an x squared here. You have the same thing here. The only difference is the z square and the x square have a 1 multiplying it. So the first thing you want to do here to make this problem easier for you is to get rid of that -2 and make it a 1 by dividing it on both sides. And you get x minus 7 squared is 10. Okay. Now I'm going to use an idea that I just showed you with whenever I have a square equal to a constant, I can take the square roots of both sides as long as I remember to put a plus and minus in front of the square root of the constant. So I'm going to take the square root of the left side and the square root of the right side, but I'm going to remember to put the plus and minus there. And now I just add 7 to both sides, and there's my 2 answers. And I'm done. I can. I'm just showing you the fastest way. Okay? I'm not showing you the way that you would intuitively doing it. I'm trying to have you see that when you have a perfect square on one side, it doesn't have to just be a little single letter like x and z. It can be a quantity, and you can still take the square root of both sides. As long as you remember to put I'll do it for you your other way. Just hang on a minute. Anna? I will do it 2 other ways for you, okay? Okay. But do you see that part of expanding your view is to train yourself that when you see something like this, the x minus 7, that quantity square, it's really no different than A and B. It's still a perfect square on that side. So you don't have to square the whole thing out. And then you don't have to subtract 10 from both sides. And then you don't have to either factor or use a quadratic formula. You can get there very quickly by dividing both sides by whatever the coefficient is, square rooting and remembering the plus and minus, and then solving for x. So it can really be 3 steps. All right, so let's take a look at what most students do. Most students, when they see this, they haven't trained themselves to recognize that this is simply something squared equals a constant. The things that get in their way are this: the -2 out front and the fact that this is a binomial being squared. So it messes with their minds, okay? So the wrong thing to do here, this is what I sometimes hear students do. They say, oh, I'll multiply -2 times this. You can't do that because you got a square here. So you could multiply the -2 first if you wanted to. I wouldn't recommend it, because what's going on here on the left-hand side is you have a multiplication problem of 3 factors. You have a choice, folks. You could first multiply the -2 times x minus 7 if you wanted. Take that answer and FOIL it with x minus 7. This is the associative property. When you have the choice to multiply 3 things, you can multiply any 2 first, find the answer, and multiply it by the third. In this particular case, since you have a perfect square, you might as well square this binomial, then multiply it by -2. But again, that's what most of you do, because most of you forget this very first step that makes life so much easier, is to just make it a 1. So I got x minus 7 times x minus 7 equals 10. And then I'm hoping no one ever leaves this class and says that when I square this, I get x squared plus 49. I hope by the time you leave here, you don't square a binomial that way. This is x squared minus 14x plus 49 equals 10. The only way I can solve this now is to subtract 10 from both sides. I cannot factor this, so the only way I can now solve this quadratic equation is with the quadratic formula. So a lot more steps than what I just showed you a minute ago. Okay, the choice is yours. I don't really care which way you do it. It's totally your choice. So let's use the quadratic equation on this. So what's A equal in this case? What's A going to be here? 1. B is equal to negative 14. And C is equal to 39. So x equals negative b plus or minus the square root of b squared, 14 squared, 14 squared. Negative 14 squared is still the same as 14 squared. What is that? 14 squared. Plus or minus the square root of 196 minus 4ac all over 2a. All right, what's 4 times 139? 4 times 39. Oh, here we go. 4 times 39 is 4 times 40, which is 160 minus 4. It's 136. Plus some. Oh, you're right. 160 minus 4 is 156. You're right. 196 minus 156 all over 2. That's what I get for trying to show off. X equals 14 plus or minus the square root of 40 all over 2. You leave it here, you don't get full credit. Why not? You haven't simplified it. So there's 2 answers here. Here's one answer. And here's your other answer. Or remind me to tell you what you have to do in my math lab as well. Okay. So you say, I see, and do not make the mistake of canceling that 2 and the 14 and leaving it, because that's not finding a common factor. This 2 is the denominator for 14. It's also the like denominator for the square root of 40. So in other words, to get that single fraction, I would have had to add these 2 numbers. That 2 belongs to both of them, so don't dare take it away unless you find a 2 common to both, the 14 and the square root of 40, which we might do. All right, so let's simplify the square root of 40. Hopefully we're getting a little more familiar with this. What's the square root of 40? It's the square root of 4 times the square root of 10. And what's the square root of 4? 2. 2 square roots of 10. Ooh, I see a 2 common now. So we get 14 plus 2 square roots of 10 over 2. So that means I really got 14 plus or minus 2 square roots of 2. So I'm just going to change this back to my 2 answers, plus or minus, because you always will have conjugates for your answers. Okay. Or excuse me, opposites for your answers. So we get 14 plus 2 square roots of 10 over 2 and 14 minus. So can I simplify this? Is there a common factor to everything? Yes, it's 2. I can pull a 2 out of the top and get 7 plus or minus the square root of 10. And I can pull a 2 out of the bottom. It's just sitting there. And now I can cancel a common factor of 1. Get my arrow back. Boom, boom. There's my 1. So my answer is x equals 7 plus or minus the square root of 10. I don't know about you, but the first way I did that was a lot quicker and efficient. But if you don't see it, then rely on the long way if you have to. Okay? Now, I want to tell you something about solving quadratic equations. And you may think that this is sort of a picayune kind of thing. But I want you to go back and I want you to look at what you have here for your work. Some of you who maybe turn this into x z squared minus 9, let me show you something. If you do this, and then you come down and you do this, and then you come down and you write this, you will not get full credit. Why not? There's no equal sign. This is an equation. From the very first equation you ever solved in algebra, whether it was as simple as x plus 5 equals 7, when you wrote the next equation underneath, which is the answer, it's an equation. You solve an equation with an equivalent equation. So you have to put this in. These are equivalent equations. You have to put this in. Otherwise, you can't do it. Z squared minus 9 has no answer. You can certainly factor it, but z plus 3 times z minus 3 has no answer until you say what it's equal to. So go back and correct any of your work to make sure that at each and every step of solving the equation, you see another equation. That's something that I'm really sort of, we've talked about this property. And so what we have left is, notice I've given you very specific instructions now. I've asked you to solve these by factoring. And then 14, here's a song, we've already done it. 14, I asked you to do these by quadratic formula. So look over those 5 problems, do however many you can in the last 10 minutes, and if you have questions, let me know, put up your flag, okay? My math lab, let's go back here. So if you're going to enter the answers in my math lab, so let's go back to z squared equals 9. Remember, they're going to give you the little teeny like solution set, right? That you're going to see something like this in my math lab. And you've got to put the answers in -3 and 3. You always put your smallest number first, or your smaller in this case, since we only have 1, 2. So you would write it this way, -3, 3. If you write 3, -3, it's going to tell you you're wrong. So just put the smaller number first anytime you have more than one solution. Okay? Thanks for reminding me, Tom.